Okay, so right now I want to talk about the twin ruler paradox. Now, what exactly is the twin ruler paradox? Okay, it goes like this. You have two rulers, each 1 light years in length. We can call them light year rulers. And all of a sudden, one ruler starts moving towards the other one. Now, when one ruler is moving, both rulers will interpret the other ruler as having length contraction. And once the two rulers pass each other, they would both have moved the same distance, right? Which would be the distance of the other ruler. So it will look something like this. From A's perspective, A would see B as contracting in length and then moving to the left. From B's perspective, B will see A as contracting in length and then moving to the right. They would both see the exact same thing. They have symmetry. Because they have symmetry, how can there be a paradox? In the sense that, how can we determine who's moving and who's not? This goes back to the twin paradox question. Now, this is an implicit assumption of they have symmetry. Now, why do we think they have symmetry? We think they have symmetry is both rulers are contracting in length. So, because B sees A's ruler as being contracting to 0.8 light years, again, they're moving at 0.6 c. So, the length contraction of 1 light year will be to 0.8 light years. A will see the exact same thing. That's why we might think they have symmetry. But the truth is, they don't actually have symmetry. And I will explain why that is not the case and how to solve and resolve this paradox. So, to understand how to solve this paradox, we must understand a very critical thing. Now, in space, we have 3 things. We have time, we have distance, and we have velocity. Now, right now, everybody agrees on velocity. Both A and B interprets the other one as moving 0.6 c, so that is constant. But what they are going to disagree on is position. They do agree on distance. Okay, so to fully understand how to solve this paradox, we must understand one thing. So in space, we have 3 things. We have distance, time, and velocity. Now, velocity is constant in the sense that both sides, both A and B, interprets the other one as moving 0.6 c. So we know that's constant. And we also interpret distance as being constant in the sense that both distances have now contracted, right? Both rulers have now contracted to 0.8 light years. That's a fundamental reason why there is a paradox. Because if they both see each other as contracting down in length, how could we possibly resolve the stationary and the moving object? But what they're going to disagree on is positioning. Yes, they technically agree on length, but they disagree on positioning, and I will explain why. So, now, the first question I'm going to propose is, let's suppose we have an object contracting in length due to motion. In what direction is that object going to contract in length? It has to contract in a direction, but is that going to contract to the left or the right?
Let's suppose we have 2 objects here. Well, let's say these are the same objects, or 2 identical objects, it doesn't matter. So, the question is, when something starts moving really fast and it contracts in length, where is that center point, or the point of origin of that contraction? So what does that mean? So what does that question mean? So let's suppose that this object starts moving really fast. Now all of a sudden it goes from not moving at all to half the speed of light. Now we know it will contract in length. So will it contract in length this way? Or will it contract in length this way? Now where's that difference? Again, I'm using this as the control group. I'm kind of showing you where that difference of that contraction is. So the second example, I'm using the right side. So it contracts to the right. In the first example, it's contracting to the left. This makes a huge difference. The answer, of course, is very simple. The center point, or the point of origin of that length contraction, will, of course, down to the center of it. So it's going to contract this way. So now notice, from the original piece of paper, there's now a gap on both sides. So it's not contracting to the left, it's not contracting to the right. It's, of course, again, as I said, it contracts to the middle. So the middle, or center point, is that origin or center of that length contraction. And this makes a huge difference in our example. This also affects the pole and barn paradox. And this is why. Because there's a different origin of that contraction. So let's take a step back and let's say that what if we are on a moving object? Let's say we're on a train and we're moving really, really fast. Now, of course, the train track, in this case, would contract in length, the entire train track. And where would the point of origin of that length contraction be? Now, technically, the train track isn't moving, but to our perspective, since we're on a train, we're on a super fast moving train, we think that train track is moving. So, in this example, the center point of that length contraction, of the train track, to our perspective, would be, of course, to ourselves, to where we are on the observer. So, if we're here, then we would see the train track contracting this way. Again, imagine this is a much longer train track. I only have this short piece of paper. On the other hand, if we're here, then we're going to see the center point, the contract this way. So, and it depends on where we are on the train, of course, where that center point of that length contraction occurs. Because again, technically, the train isn't moving, it's us that's moving. In fact, it makes it even simpler to imagine the train as not being a train, but just a point on the train. We're just a simple point on the train. Let's suppose we're here. We're a simple point on that train. And where we are on the train is where we would visualize our sort of center point of our line contraction. Because technically, even though the train track isn't moving, we see the train track is moving. And the train track will always be moving to our perspective. And as I said, depending on where you are on that train, you would see, the center point of that line contraction is in a different location.
Okay, so that does make sense. When we observe a moving object, so let's say this object is moving to the left, that object will contract down the middle. Okay, now here's the thing. We also have a scenario in which both rulers are going to move to each other at the same speed. In that case, there's obviously no paradox because there'd be perfect symmetry. They're both moving at the same velocity. So the only problem comes up when one is stationary, the other's moving, or they're moving at different speeds. So in this case, we're saying A is stationary and B is moving. And we're trying to solve how to figure out B is the one that's moving and what exactly they're going to see. And the implicit assumption is that they're going to see the exact same thing to each other, just in opposite directions. And the answer is that that is not the truth. They're going to see different things because they're going to disagree on positioning. So I am going to show you why. Okay, so as like I said, during line contraction, the object that's moving will contract down the middle. So from A's perspective, let's suppose we're on A and we're going to see B. Now, for the sake of this example, we're going to add 2 more frames of reference to make it easier to understand. So we're going to add M, which would be the midpoint of B's ruler. We're going to add C, which would be the leftmost point of B's ruler. Through these 2 frames of reference, we can actually understand how this line contraction is going to happen. So, from A's perspective, remember, before anything moves, both rulers were touching. They're both the same distance, the same length. But, as soon as the B's ruler starts to move, that ruler contracts in length, and we know that. But, it contracts in length through its center point, through the middle. So, from 1 light year, it contracts to 0.8 light years. Therefore, it will contract from both directions. Now, 1 subtract 0.8 is obviously 0.2, but they're contracting from both left and right. So from each direction, there'll be a contracted length of 0.1. So now, between C and A's ruler, we will have a gap of 0.1 light years. Okay, notice that gap. This number is going to come up again. In this case, we have 2 small gaps. Okay, so next, we are going to look at B's perspective. B's perspective is actually the most complicated one. Okay, so now, what is the total distance of this whole system? Well, it's 2 light years, right? Because there's 1 light year here, 1 light year. The whole distance is 2 light years. So let's look at B's perspective. From B's perspective, length contraction goes to the center. But since B is the moving object, length contraction goes to B itself. Not to C, not to M, but to B. So the entire distance of 2 light years, which was here, contracts to 1.6 for B's reference point. Then it's a matter of figuring out what this number here is. Now, when this length contraction occurs from B's frame of reference, what will he see? Will he see the 2 rulers as touching, overlapping, or will they see a gap? Remember, we know A sees a gap. Well, it's a very simple math to calculate, right? So, the leftmost side of A is 2 light years away from B. We know that, right? So from B to A, this whole distance is 2 light years. So, when B starts to move, this 2 light year distance contracts down to 1.6 light years. Very simple math. Now, what is the distance here? Well, it's very straightforward. B will see A's distance as being 0.8 light years. Why is that? Because A has also contracted in length. Because again, B is moving, so B sees A as the one in motion. So A, which is 1 light years, contracted to 0.8 light years. And it's a very simple matter of subtraction. 1.6 light years, subtract 0.8, equals 0.8 light years. So the right side, the rightmost point of A is actually 0.8 light years away from B. Right? 1.6, subtract 0.2. So, but B also sees the distance of C. The BC distance is 1 light years. Because B and C are in the same system, B obviously will not see C as contracting length. So this distance is still 1 light years. Therefore, we have an overlap of 0.2 light years. Notice, from A's perspective, A sees a gap of 0.1. But B's perspective, B sees an overlap of 0.2. Right there, symmetry breaks. Symmetry breaks right here and then. But we're going to take a look at C's perspective. And what does C see? Okay, now from C's perspective, remember, C will see everything contracting length. But C is the point of origin of that length contraction. So C will see length contraction from both sides. So for example, if there was, let's suppose that there was some sort of imaginary point here, B, a space station or something, 1 light year away from C, right aligned with B, then naturally that will contract down in length too. Well, that distance to that space station will contract down. And from A's perspective, there will also be a length contraction. Okay, now, how do we calculate this length contraction? Well, it's not particularly hard. let's take a look. So, in the initial position, before everything starts to move, A is 1 light years away from C. So, when C, or B, or M, or whatever, starts to move, that 1 light year distance length contracts to 0.8. Which is, again, so this is the center point, that contracts to 0.8. But again, if anything's to the right of A, C will also contract down. So, this total distance, which is once 2 light years, for the whole system, is now 1.6 for C. Most notably, the distance from C to A is now 0.8 light years. Oh, that's C's perspective, B's perspective. So from C's perspective, that's now 0.8 light years. Okay, but that's it. But, most notably, C and A are still touching, or C and A's ruler are still touching. Remember, the original position, C and A's ruler were touching. From A's perspective, there is a gap between C and A's ruler. From B's perspective, there's an overlap between the two rulers. But from C's perspective, there is still no gap nor overlap. Well, why is that? Well, it's simple length contraction. The length contraction of 1 light year becomes 0.8 when there's a velocity of 0.6 c. What is the length contraction of 0? Well, it's 0. Because C and A's ruler are already touching at a distance of 0, that distance obviously is only going to contract ever down to a 0. A 0 contracting distance will always stay 0. So that distance never changes. It's still going to be a 0. But A has now contracted 0.8. Okay, so notice the 3 asymmetrical viewpoints. A sees a gap of 0.1. B sees an overlap of 0.2, where C sees the 3 objects touching. Now, what's really cool is that these numbers will show up again, as I promised. Now, why is that? Okay, so, as I said, the numbers will show up. The 0.1 number to be keep note of, because it will show up again. Now, where's that 0.2 go? Well, that 0.2 is now here, creating a gap here between the edge of here. So, again, assuming there was a space station over there, in the original position, there was a space station here that C can take to use as a point of reference. That space station's distance would have contracted down here, which is 0.8 light years away from C. Again, C, this whole system is from 2 light years to 1.6 from C's perspective. So there's now a 0.2 light year gap between this one from that boundary. From A's perspective, there was 2 0.1 light year gaps. Again, if we add that up, that's 0.2. From B's perspective, there's a 0.2 light year overlap. Notice the same number occurs 3 times, but in different contexts. A sees 2 0.1 gaps, B sees a 0.2 overlap, while C sees a sort of opposite end 0.2 gap. Okay, so if that's not enough to convince you guys, let's look at the final position and the total distance traveled. So, what happens when this whole system clears? So, when C and B's sort of ruler passes A entirely, and B will meet A. Now, to figure out what happens is, first of all, is that we don't really know if there's going to be simultaneous events. So the only way to determine if something ends is when B thinks B has reached A. So, the total distance traveled. So when B hits here. Now, okay, so next we're going to do is, for those who are unconvinced of all these numbers, let's look at what happens at the very end of the system, when everything is fully traveled through. What happens when the system stops, when B reaches A. Okay, so let's look at what happens. So, the moment B reaches A, everything will stop and we'll calculate all our numbers. Okay, so specifically, this will be the point just before everything stops. So, at the moment, so everything's still moving, but we take a snapshot just before B reaches A, or B thinks it's reached A, and we take a snapshot there and look at all 3 perspectives at that exact moment. Because the thing is, as soon as B and C stops moving, or if they stop moving at all, then length will uncontract. We get back down to this sort of new sort of system. But right now, we'll have this sort of contracted distance. Okay, so first is we'll look at B's perspective. Okay, so this is what B will kind of see. B will see itself touching A. Now, how far would B have traveled to his own perspective? Well, we know from earlier that this distance is 1.6 light years from B's perspective. Remember, that 2 light years has contracted to 1.6. So B, technically, from his perspective, only travels for 1.6 light years. Again, you could also say B is stationary and A is traveling. But again, it's the same thing. It will still travel for 1.6 light years. So this journey is 1.6 light years. Okay, so now notice how they have no symmetry. And because if they have no symmetry, then there is no paradox. They see different things. Now, they agree on the length of the other object, and they agree on velocity. But they disagree on the positioning of these objects, of these rulers. Okay, so that's how we resolve the paradox. You see, yes, they agree on velocity and they agree on the length of the other object, but they disagree on positioning. Remember, A sees a gap of 0.1, B sees an overlap of 0.2, while C sees that they're touching. And that resolves paradox. So that's the solution to the roller paradox. Again, it's the same thing as a twin paradox. All you do is take a look at the different perspectives and see if they actually see the same thing. And we can see that they have no symmetry. They see different things, they observe different things, therefore we can conclude why there is no paradox. And that we can say which one's stationary and which one's moving. Okay, so next is, this should be the end of it. But I just want to kind of add a bit more to kind of show you guys what happens at the end of this journey, at the end of this sort of example. So when B has fully passed A. Now we know the original position, the initial position, they have different interpretations of distance. And that's exactly why there's no paradox. But what exactly happens when B has reaches A? When B's ruler fully passes A's ruler? I just want to show you guys that as a sort of a bonus section in this. Okay, so the first thing is obviously we can just figure out what is actually the time and of our journeys here. So from A's perspective, since A would see B move for 2 light years at 0.6 c, that would be 3.33 years. Now, if we plug this number in, 3.33 years, into a time dilation calculator, we'll realize that from B's perspective, because he's in motion, same with C, they will both experience a dilated time of 2.67 years. Now, this number is going to come up again, which is why I kind of want to show it right now. Okay, so the first we're going to look at is B's perspective. So from B's perspective, what happens to B's perspective at the very end of his journey? So this would be just at the point as he's passing A, but before he stops. Now, or if he stops at all, we don't know if he's going to stop, but we'll just say for now that as soon as he passes A, before he stops, we're going to have a snapshot of what he sees. Okay, so what does he see? The first thing is, he's going to see a distance of 0.8 light years. Naturally, because again, A has length contracted from 1 light year to 0.8 light years. Next is that this total journey, how far has B actually traveled? Well, we know that from earlier. From B's perspective, the distance between B and A at t equals 0, just as he starts to move, is 1.6 light years. Now, the original distance is 2, but again, due to length contraction, it contracts down to 1.6 light years. So we also know that, given that at the beginning, A is 1.6 light years away from B, B's journey must have taken 1.6 light years to reach A, because B has to travel that distance to reach A. So at this point, when B touches A, B has journeyed for 1.6 light years. But A is 0.8 light years. The end of A, the other end of A, is 0.8 light years away. So this is what B sees. Okay, now, that 0.2 light year gap is also the same thing, right? This is 1.6. Now, this distance here. So how far is C from the end of A right now? From the right side of A right now? Well, C and B is 1 light years. We know that. Because, again, their object is 1 light years, and obviously B doesn't see his own ship contracting in length. So 1 plus 0.8 is 1.8. So this total distance, so the right side of A to C is 1.8. So there's a sort of a gap thing here of 0.2. This will be the the length contraction gap. Obviously, because B from the real space has contracted to 0.8 to the left of B, but C is still 1 light years away from B. So there's a 0.2 light year gap. I hope that's not too confusing, but the point is B has traveled for 1.6 light years, and B is touching A right now. So then we're going to look at C's perspective and A's perspective. Notice that they do not agree on the same thing. Just as at the beginning. See, the initial conditions, B sees the overlap, C sees a touching point, while A sees a gap. Again, at the end point, they will also see 3 different observations. Okay, so we're going to look at C's perspective, and C's perspective is the most difficult one to figure out. So this is kind of the initial conditions before everyone starts moving. Again, so we have A here, which is, again, 1 light year ruler. C and B are 1 light years. And again, total distance is 2 light years. So how do we determine when B hits A? From C's perspective, C doesn't actually know when B hits A. Yes, C might see B hits A, but that's not simultaneous with B hitting A. So for that, what C needs to take a snapshot of is, well, B can tell C when to take a snapshot, or B can estimate when that snapshot is going to take place. So now, we know B travels for 2 light years, so when C also travels for 2 light years, then B and C would agree, then presumably B would have touched A from his perspective, right? So let's pretend we're C right now. When we're traveling, how do we know that B thinks he's reached A? Well, again, at the 2 light year mark, because B would have traveled for 2 light years, then C would also travel for 2 light years. So we have an imaginary point I here to kind of estimate. So when C hits this imaginary point in space, that's when C is going to take that snapshot. Okay, so it's going to look something like this. So a t prime of 2.67 years. Okay, so this number here. Before everybody gets confused, again, we know B has traveled for 1.6 light years at a velocity of 0.6 c. Or B sees A traveling for that distance at B station. It doesn't matter. So when we plug that number in, it becomes 2.67 years. So that's 1.6 divided 0.6 equals 2.67. So to C's perspective, the same amount of time would have passed, 2.67 years. So in this regard, what exactly would C see? Well, C would be a imaginary point I, which is this point here we established at the beginning. Now the dilated distance would be 1.6 light years, as in this is how much C has traveled. C has traveled for 1.6 light years, exactly the same as B. So B has traveled for the same amount of distance at the same amount of time, which is 2.67 years. But now let's look at this overlap here and why this exists. Well, it's very simple. How far away is A to C right now? Well, it's 0.8 light years, right? Because C has traveled for 1.6 light years, and A is also 0.8 light years in length according to C. So A would be, again, at the halfway point, so C is 0.8 light years away from C right now. So this distance here, from A to C, is 0.8 light years. From A to the other end of A would also be 0.8 light years. But C to B has a distance of 1 light years. Again, because that's how far they are. So B is further away from A than C is. So how it goes is C, and then he'll see A, and then B. B is the furthest point here. So there's an overlap of 0.2 light years. Again, see, this is another time where symmetry breaks. At the beginning of the system, in the initial conditions, we have breaking symmetry, because again, they see different things. But, again, right, because there's an overlap here for B's perspective, and touching for C's perspective. But, at the very end of our journey, there's also a break in symmetry. So B sees a touching point, but C sees an overlap. Again, C thinks A is actually closer to B. Closer to them than B is. Now, if we go to A's perspective, what does A see? Well, A's perspective is actually pretty straightforward. A would see B, or in this case M, actually, realistically, this object travel for 2 light years. Because again, that's the total distance. Because that would be the total distance the other object would have to travel. So A would actually see B past them and creating a gap of 0.1 light years. Now, remember, there will be a gap here. Now, why is that? Because we look at the initial conditions. What does A see at the beginning? A sees this, right? A sees a gap of 0.1 light years right here between the two. So when this object, when the ship, CBM or whatever we're going to call it, travels for 2 light years to the left, it is 2 light years. Travels for 2 light years to the left, because again, A is 1 light years in length. It travels 2 light years to the left. They would again have this gap here. So there's now a gap. So again, just at the beginning, when we have 3 asymmetrical viewpoints, at the very end, we also have 3 asymmetrical viewpoints. So again, from B's perspective, there's touching. So B at the beginning sees an overlap. At the end, he sees touching. From C, at the beginning, C sees touching. But at the very end, C sees an overlap. But for A, for both perspectives, from both beginning and A sees the same gap, 0.1. And notice the numbers, right? 0.2, 2 0.1 light year gaps, a 0.2 light year overlap, and then touching. So again, all the numbers do add up, but again, in different positions. Okay, so earlier there was a different 4 years. That's actually incorrect. It's 3.333 years. It was a mistake on the diagram. Okay, so let's look at A's perspective first. So the first thing is, what exactly happens when A sees everybody stops moving? Okay, so very simple. A sees B as being 0.8 light years, but at this point, and there's a gap of 0.1 light years. Now, remember when I said that length contraction is at the center? So length uncontraction or length expansion is also at the center. So as soon as B stops to move, then it will start to uncontract in length or expand in length, and that expansion will come from the middle. So it's going to expand both to the right and the left. So in this case, it will expand to 1 light year from 0.8. So right now, 0.8 light years expand to 1 light year, the same as A, or same as the initial point, initial length, and expand from both right and left in equal distance. So then this will expand to the right as 0.1 light year gap, and it will expand to the left as 0.1 light years. So instead, remember when A saw a gap between A and B? Well, that 0.1 light year gap is now disappears because B is going to expand into A, removing that gap, so A will be touching. Just like this, right? There's no gap anymore. Okay, so next, let's look at B's perspective. Okay, so B's perspective, this is a kind of a complicated diagram, but let me just run through what this means. Okay, so we know that B has traveled for 1.6 light years. And we also know that A was 0.8 light years away from B at the end of this. So as soon as B stops to move, then we have length expansion again, or length uncontraction. But where is that origin point of that length contraction? Well, it would be to itself, right? Because whenever an object is moving, then the length contraction will originate from the observer on that object. Not the object itself, not the midpoint of that object, not the left side of the object, not the right side. It will be the exact observation point of the object. So it will be at B. So B will see the entire universe expand in length in both directions, left and right. So this 1.6 light years will expand to the right and left to 2 light years. So naturally, see these two 0.2 light year gaps will then, again, will expand to the right and left. Now, most specifically regarding A is 0.8 light years in dilated contracted distance. When B stops to move and A uncontracts in length, from B's perspective, A will expand back to 1 light year. So again, see that? So A will, from B's perspective, A will expand to 1 light year. Now, B and A are already touching, so this position doesn't change. So B and A are touching. And again, as I said, because at a distance of 0, there's no length contraction. Similarly, at a distance of 0, there's no length expansion or length uncontraction either. A cannot get further away from B or closer to B because, again, their distance is already 0 at this point. There's no gap between the two. So A will expand to the right, from B's perspective, expand to the right at 1 light year. Now, C's perspective is probably more complicated than B's perspective. So what happens whenever B stops moving and C sees the universe uncontract in length? Okay, let's look at this for a moment. Now, remember I said the center point of that length contraction is at the origin, which is right here, which is right where C is. So C will see the universe expand in length from the left and the right. Now, note this, that we don't actually have anything to the left of C in our example, so we're going to ignore that. But C will still see all of this distance expand to the right. So remember, C traveled a journey of 1.6 light years. Now, had there been, let's say there is a space station or something over here, or in this case, we'll just see the right side of A. So all of this distance will expand from 1.6 to 2 light years. So let's look at the right side of A. The right side of A in this case, which is right now, when C is still moving, when everything's still moving, the right side of A, as I said earlier, is 1.6 light years away from C. Because again, that's how much C has moved. If you're not sure about that number, I think this picture kind of shows how that kind of works, right? So this is the initial position, going to the right, left, and we have that imaginary point. So when C reaches the end at imaginary point, A would have to be 1.6 light years away, because C originates on the right side of A, right? C was at the right side of A at the very beginning, and C travels for 1.6 light years to the left. So right now, the right side of A is 1.6 light years away from C, just to kind of make sure you guys understand where that number comes from. Okay, so again, we get here, the right side of A is 1.6 light years away from C. Okay, and A has a distance of 0.8 light years. First of all, the length contraction of this entire dimension goes to the right, to 2 light years. So, the right side of A will now be 2 light years away from C. Right, got that 1.6 becomes 2. Now, remember, C saw an overlap between B and A, right? So A is closer to C than B is. The gap overlap. So, when the right side of A expands over there, and then, what happens then? Then A, at the same time, A will expand from 0.8 light years to 1 light years. So, again, the right side of A is 2 light years away, and A is 1 light year away, then therefore, the A itself, so the left side of this ruler, will be exactly 1 light year away from C. So, we get back to initial position. Notice how all three parties now see the same thing, right? Because when everyone stops moving, everyone sees the same thing. But again, their expansion occurs differently. From B's point of view, the length expands from both directions. From A's point of view, this ship itself, this ruler, has expanded in length. From C's perspective, everything expands to the right. Now, technically, again, C is the center point of that expansion, so there will be expansion on the left side as well. But again, for this picture, we only see the right side expansion for C. So again, they now see the same thing. So when everyone stops, all observers now see the exact same thing. So let's take a step back of this journey to kind of summarize what everyone saw. So this is the initial position, in which case there's two rulers like this. And B ruler will move to the left. So that's what we saw, right? And B will stop once B has hit A. So once this ruler fully passes that ruler. And we have time dilation calculations here from here. And again, if we add these numbers up, it will actually add up. And these numbers will actually fully match. When we put in the length contraction, contracted distances, and plug in the velocities, the numbers do add up. Okay, so B will move to the left, and as soon as B hits A, when this ruler has passed the other ruler of 1 light years in length, it will stop moving. Okay, and at t equals 0, everybody starts to move. So in this case, the B ruler starts to move to the left. So because of that, A sees the B ruler length contract along its center, creating two 0.1 light year gaps, while the ruler itself becomes 0.8 light years. B sees something slightly different. B, however, also sees A's ruler contracting to 0.8 light years. B agrees with that. However, what B disagrees on is the positioning of A's ruler. So for B's perspective, there's an overlap of 0.2 light years, in which case, B actually sees the ruler as being closer to itself than C is. So again, B sees this ruler closer to it than C. This distance is 0.8 light years, is shorter than the distance that B interprets the BC difference, which is BC distance, which is 1 light. From C's perspective, is slightly different. C, however, sees that both rulers are actually touching still. Because again, at the initial position, which C and C is touching the right end of the A ruler. So at 0 light year distance, length contracted will still be a 0. There is no difference in that length contraction. So C sees touching. B sees an overlap. A sees a small gap. B sees the length expansion starting from itself to the right and left of the system to getting back to initial position, getting back to this final position. C also sees the length expansion, but to the right, getting back to this position. Whereas from A's perspective, however, now just as we're traveling to the very end, just before the B ruler stops moving, we still see 3 asymmetrical viewpoints. Again, there is no symmetry. Just as the initial position, there's no symmetry, at the end position, or the near end position, also has no symmetry. B sees that there is touching A. C sees an overlap in this time. Well, A still sees two 0.1 light year gaps. The numbers do add up, but A kind of sees them twice in two smaller gaps, whereas B sees, or C in this case, sees a larger overlap. Now, as soon as everyone stops moving, A, of course, also sees the B and C ruler expanding in length, getting back to, again, closing that gap, and getting back to the initial position, or the final position. So again, all three, in this case at the very end, when everyone stops moving, all three observers now agree on the same thing. But notice how during the entire journeys, there is no symmetry. Everybody sees something slightly different. They agree on the velocity, they agree on the length of the other object, but they disagree on the positioning of the other object. And that is how we solve the twin ladder paradox. Again, there is no paradox. We have figured out that they have asymmetrical viewpoints, and that is why there is not a paradox. Okay, so I hope that wasn't too complicated, and I hope you guys liked the video. Thanks for watching. Please share.